recall the harmonic oscillator that we studied just a few videos ago. So, there we considered a problem where we had a quantum particle which was in a potential something like this. If I plot x versus the potential energy, and this is a function half m omega square x square, which represents the potential. It is also called as the potential of the harmonic oscillator. And now, when we are considering a quantum particle in such a potential, we are now focusing on what is called as a quantum harmonic oscillator. In this, the allowed energy levels are given by this operator h cap, which is given as p cap square by 2m plus half m omega square x cap square. And we saw that the solutions to these are these states which give us these solutions where n equal to 0, 1, 2, and so on. And this en, e0, e1, e2, and so on are all equally spaced energy levels of this quantum harmonic oscillator. We saw that this particular operator can be written as, by converting these by using a transformation with the momentum and the position into creation and annihilation operators, we get this h cap to be of the form half h cross omega a dagger a cap plus half. Sorry, this is h cross omega a cap dagger a cap plus half. We had also seen that this a cap dagger a cap, when it acts on n, gives us n times n, and we called this as the number operator. But we didn't understand why these are called as creation and annihilation operators. Now let us understand what they would do individually when they act on these, what are called as the number states or the single mode Fock states, which we saw when we generalized this into the Fock space. So let us say that when, let us start with the annihilation operator. And let us say that when an annihilation operator, this denoted by a cap, acts on the number state, it gives you root of n into n minus 1. We will justify why we do this in a few seconds. So, because it takes this particular state n to n minus 1, we call this operator as a annihilation operator. Another thing with this annihilation operator is that we consider that this gives you zero state back again. So it cannot go, this number cannot go below 0. Now, if we have multimode Fock state, then if you want to understand how this number operator will act, let us take an example. So if this is the multimode Fock state, nk1, nk2, nki, nkj, nkm, so this I will act, a cap ki will act on this particular part of the Fock state, and this will act on this particular mode of the Fock state. So this will give me root of nki, root of nkj, and k1 and k2 up to nki minus 1 and kj minus 1 up to nkm. So this is how it will work for multimode Fock states. Now let us consider the creation operator, and let us define what it will do. So this creation operator, we say that when it acts on the number state, it will give me n plus 1, root of n plus 1 into n plus 1, and it will act in the same manner for the multimode Fock states in the same way. So I leave it on you to understand how it will work. Now, I said that I will justify why this kind of a decomposition or this definitions work. So let's say I use these both definitions and I act a dagger a on n. So let's first act a on n. It will give me a dagger into root of n into n minus 1 according to the definition. Now, because this is a number, I can take it over here. So this will become root of n into a dagger n minus 1, and this will give me root of n square into n, which is equal to n into n. So this kind of a decomposition is justified by our definition of what this operator a dagger a, which is we also called as n cap, does. So now we understand that this is what a creation annihilation operator do when it acts on a number state, and this is what the creation operator will do when it acts on the number state. Now there are some properties of these number states or these operators which are important. One, that both are non-Hermitian. Both are non-Hermitian operators. By non-Hermitian I mean that a dagger or any general operator O dagger is not equal to O. You can easily see that when I take A dagger is not equal to A, because they have different kind of an operation when it acts on the number state. So they are not same. Second is that n cap is equal to A cap dagger A cap, such that n cap acting on n will give me n into n. Third is that A cap dagger A cap dagger is equal to A cap equal to 0, and A cap comma A dagger is equal to minus of A cap dagger A cap equal to 1. So these are the commutator properties which are important. They are easy to derive, and I will not go into it. I highly recommend you to understand what is a commutation relation if you are not familiar with quantum mechanics. Yeah. Let us understand the matrix representation of these operators. So, as we saw that the number states can be written in this manner, and so on. We can write these operators A dagger and A as square matrices which are infinite cross infinite, if these are infinite cross one matrice column vectors, and the elements of these matrices are 0 0 0 up to 0, root 1 0 0 up to 0, 0, root 2 0 to 0, and this will keep on going and so on. Now in the same way, we will have, we can write the matrix A cap as 0, root 1 0 0 0, 0 0, root 2 0 0, 0 0 0, root 3 up to 0 and 0, and this will also be an infinite cross infinite matrix. Now we need to understand that in this case, uh, the non-zero elements will be on the, what we can call as the lower off diagonal, and in this case the non-zero elements will be on the upper off diagonal, and the diagonal elements and everything else will be zero when we represent. Now let us check our claim if we are right or wrong. So let's consider a dagger acting on the one state. Let us write the matrix representations. So this is 0 0 0 up to 0, root 1 0 0 up to 0, 0 root 2 0 up to 0, and this will go up to 0 and so on. And this will act on 0 1 0 up to 0. This is an infinite cross 1 matrix. This is also an infinite cross 1 matrix if you don't have any cutoff dimensions. And when you act on this, you will get root 2, or let me write it this way, 0 root 2, oh sorry, 0 0 root 2 0 0. Again, infinite cross 1 matrix. And you can write this as root 2 into 2. This is exactly what a creation operator will do when it acts on this number state 1. So this matrix representation is indeed valid. Now let us understand the higher order Fock states, how they can be represented. Let us start iteratively. So we saw that when we act a dagger on 0, we will get root of 1 into 1. When I will act a dagger on 1, I will get root of 2 into 2 state. This can also be written as a dagger acting on a dagger acting on 0 is equal to root of 2 into root of 1 into 2. If I act a dagger on 2, I will get this is equal to root of 3 into 3. That means if I act a dagger on a dagger, a dagger 0, I will get this to be equal to root of 3 into root of 2 into root of 1 into 3. Now you see this pattern that is occurring here. So I can write the state 3 as equal to, if I combine these together and I combine these together, I can write this as a dagger raised to 3 divided by root of 3 factorial into the state 0. Now, in the same way, if I want to write state n, I can write it as a dagger raised to n divided by root of n factorial into 0. So I can generate any higher order Fock state from the vacuum state by applying these creation operators and times and then normalizing with this particular factor. So this is, however, for a single mode Fock state. If I have multi-mode Fock states, let's say two-mode Fock state, something like this, then this can also be decomposed in this manner. nk1 divided by root of nk1 factorial 0 tensor product a dagger raised to nk2 by root of nk2 factorial 0, and then even higher mode Fock states I can decompose in this manner. So this is one important formula which could be required, which will be required later on. So this is how we generate higher mode Fox, higher order, higher number states. Now let us look at what are called as quadrature operators, and we will write the dimensional less form of it. So the quadrature operators are x cap and p cap, where x cap is given as h bar by 2 a cap plus a cap dagger. If you remember, when we were studying quantum harmonic oscillator, we had an m omega term also. But as we are considering dimensionless representations, we will consider this product to be equal to 1. And p cap, in terms of the creation and annihilation operators, can be given as these. Where, as we saw earlier, that a cap and a cap dagger is equal to the commutation is 1, we can derive using this commutation relations that x cap comma p cap commutation is equal to ih bar. This is the famous uncertainty principle. I'll not derive it. And now that we have understood the relation between x cap and p cap, we can also write a cap and a cap dagger in terms of the x cap and p cap, and this is the notation for it or the expression for it. So this is how they can be written. Moreover, note that these x cap and p cap, the eigenvectors of them are not the number states. We can easily see that from here. So if I act x cap on n cap and I use this particular relation, this is equal to h bar by 2 into a cap plus a cap dagger acting on n, it will give me root of h bar by 2 a cap acting on n plus a cap dagger acting on n, and this will give me a cap acting on n should give me root of n into n minus 1, and this should give me n plus 1 into n plus 1. So you see that these number states are not eigenstates of x cap. You can similarly see that these number states are not eigenstates of p cap. So you should understand this important thing.